Screen recording, it took like an hour and 1.5 of it was just conversation.
Yes, 100%.
That's so awesome. What's poppin', Sam?
Okay, cool. So, continuous functions are used to describe how a body moves through space and the speed of chemical reaction changes with time, et cetera, et cetera. So if I'm looking at a certain point, there's 3 things we want to look at. So for an interior point, do I have this below? Kind of. Okay, so if I want to know, am I continuous at x equals 0? So at this point right here, am I continuous? Do you guys have a question? What is this? I don't know, whispering. No, it was tall. It was definitely tall whispering to Gabe. So we're looking at an interior point. So notice x equals 0, it's an interior point. What's wrong? Are you looking for a pencil?
A sticky note,
To bring your calculator next time? Never mind. I don't want to know. Okay. If we're looking at continuous, we're going to see, does the limit exist there? So that's the first question. For it to be continuous, it has to pass the 3 rules. So we went over this last year. So first we say, does the limit of f of x as x approaches 0, so the point I'm interested in, does it exist? So does this exist for my point on the left side?
Yeah.
Yes. Guess what it is? What's the limit here? -3. What's my y value? As x goes to 0 of my function, my y value is -3. Okay, second, all right, so limit exists. So I'm approaching the same number from both sides, but approaching isn't good enough. Does the function value exist there? So the second thing, to be continuous, we check if the limit exists, and then we see if the function actually exists there. Do I have a value at x equals 0? Yes. What is f of 0? -3. Awesome. And then the last thing to see, last test, if I'm going to be continuous, guess what? The function value has to equal the limit. Oh my gosh. Okay. So last I say, is the limit of f of x as x goes to 0, is it equal to the function value there?
Yes.
Yes. So guess what? I will be continuous at x equals 0. So continuity at a point, 3 things. Is there a limit? Cool. Is there a function value? Awesome. Do they match? Awesome. They all 3 things you have to pass in order to be continuous. Because I could have a limit exist. So some of you guys on your quiz, I had a limit exist, but then the function value was something else. Right? So if they didn't match, it failed. Test 3. On another quiz version, I had a limit exist, but I didn't actually have a function value. It was just a hole. So it failed the second test. And then sometimes, guess what? I picked a point where it was continuous, and I had a limit, and it passed all 3 tests. All right, so continuity at a point. So if I have an interior point, it's continuous if of its domain if the limit as I approach the number is the same thing as the function value. So I broke it down into like 3 steps, but that's what this right here is talking about. All right, for an interior point, where's my highlighter? Interior point, I have to make sure that the limit at that point is same thing as the function value. Am I approaching the same number as what the function is? And the endpoint, if it's continuous at the left endpoint or continuous at the right, as long as if I'm approaching the number from the left side is the same as if I'm approaching it from, we're more or less, we're looking at a one-sided limit. Yeah. I don't know, that was not a very good description. Okay, so the endpoint, I'll be continuous at the left endpoint if, as I'm approaching from the right side, if I'm actually approaching the same value of my function, and same way if I'm approaching from a value from the left side if it's the same as that function value. So example here is like square root function. We can look at a one-side limit to tell if it's continuous. Remember how square root functions start someplace and then they like go on? So I could look at the one-sided limit. As long as what I'm approaching is the actual function value, I could say it's continuous at an endpoint. All right, different types of discontinuity. So we discussed this, a removable discontinuity, oh my gosh, this is kind of hard to see. There's a hole right here and then the function value. So it's continuous except for this point right here. It jumps up and then I have a function value and then it like keeps going on. So an example of something like this is x plus 1 times x, what is this? All over x. Because guess what? The removable discontinuity is when x equals 0, right? If there's a factor you can cross off in top and bottom, it's removable. It's how you have the whole. We also could have a jump discontinuity. So it's like you were moving your pencil and then you literally had to pick it up and jump up and keep going. It's like a gap. It's like a stair. I should probably give you more information in just a second. So the removable discontinuity, let me go through the 3 steps of continuity at this point, x equals 0. Is this the actual function? This is. Cool. It wouldn't be. So if you plug in 0 for x, it would be 1 or 0, 1, which it is. I didn't mean to, but my example actually is the function of the graph.
But then, but how would we know that the actual point is x2?
Oh, because it's you would have to say like it would have to be a piecewise. Yeah. So you would say f of x is equal to x squared plus x over x if x does not equal 0, and then it's equal to 2 otherwise. That would be what the piecewise looks like. All right, so I wanted to go through the 3 steps of continuity just to prove to you it's not continuous. So we say the limit of f of x as x approaches 0, because that's the point I'm interested in. Does the limit exist?
Yes.
Yeah. Does the left side limit equal the right side limit?
No.
Yes, it's approaching the same number. Okay, so first we say yes, that works. Second thing, do I have a function value? Do I have a value, a y value for 0?
No.
Yep, it exists. It's 2. So guess what? Perfect. But then the third one, this is where it fails. Does f of 0 equal the limit of f of x as x approaches 0?
No.
No. So that's why it's not continuous. Because the function value is not the same as the limit. All right. So if I do the next one, I can say, does the limit as I approach f of x as x approaches 0 from the positive side, is it equal to the limit as I approach from the as I approach from the right side, is it the same as I approach from the left side?
No.
No. The limit, there's no limit. Limit does not exist here. So I know automatically it's not going to be continuous. Yes, Hannah?
Let's say we're looking at the removable discontinuity.
Yep.
All removable discontinuities fail the third test.
Not necessarily. If I have removable discontinuity, what if instead of saying, so right here, instead of saying it's 2, what if I instead went through and said, you know what, let's have it equal 1. Oh, then the function value would equal the limit.
Okay, this is be removable and focus on the y-axis.
Wait, what?
It's removable and focus on the y-axis.
So maybe something like over here. And then I still have a point right there. It'd still be removable. It would still not be continuous.
How is it like not?
It would. The one I just drew in blue would fail the third one as well. So her question was, what if, how would I not fail it? If my function value, instead of being at 2, if I made my function value 1, that would make it continuous. If I made this into a 1 instead, because then the function value would equal the limit. Yeah, because they're still removable. Well, there's still a removable discontinuity, but I have a continuous function because the one value that was not continuous, I now put in a number for it. I mean, when you take the limit, you would still get 0 over 0. Yeah. Yes, no. Yeah, you can have removable and jump as we get into like harder stuff. But right now I just want to do like one example of each of these. Okay, so now if I look at a infinite discontinuity, what happens as x gets closer and closer to 0? It goes to infinity. Okay, so let's take the limit as x approaches 0 from the left side. What am I going toward? Infinity. And then if I take the limit as x approaches 0 from the positive side, I also go towards infinity. But guess what? Saying infinity, technically that means the limit does not exist. Remember, infinity does not exist. That's not an actual number. I mean, okay, don't get into semantics with me. Infinity is a number, but it's not an actual number where I can give you a push pin and a big old number line and you like say where it is. Like, no, you can actually put your finger on it because it just keeps going on and on forever. So it's not actually a limit. I'm not approaching a single number. It just keeps going. And then lastly, an oscillating discontinuity. So as we get closer and closer and closer, it keeps switching positive, negative, and it's not getting closer and closer to one number. It's actually getting, like, the smaller steps we take, the further and further away it gets. I don't know if that makes sense to you. Because if I could zoom in way right here, you would see like it's getting closer and closer and closer together until it's like almost solid. Have you guys ever seen a graph like that? Yeah. Something like that. So sine of 1 over x. So I'm not actually approaching a single number. So I say the limit of f of x as x approaches 0 is not going to be, does not exist. So, cool. All right. So we've gone through the different types of discontinuity now, and we've gone through like what makes a point continuous. So now what we're going to do is we're going to find the intervals of continuity, the points where it's not continuous, so points of discontinuity of the function. So we're going to identify also each type of discontinuity. Lots of work. So first, let's go ahead and let's see. We always want to like factor it out and see if anything cancels out. Because if it cancels out, that means removable discontinuity. If it doesn't cancel out, guess what? I have the two factors on bottom. I can find my vertical asymptotes where there will be infinite discontinuities. Okay. So if I factor this out, this is the same thing as x plus 1 over, let's see, what multiplies 2 as negative 3. Well, that's just going to be x minus 1 and x minus 2. So nothing cancels out. So whatever's left here, I see I'll have two vertical asymptotes. So if those are my vertical asymptotes, those tell me that x cannot equal 1 and x cannot equal 2. Good luck. Woo. So those are the two values x cannot equal, so I can literally figure out my intervals of where it's continuous. It's everywhere except for where I have vertical asymptotes, because that's where it's going to be discontinuous. Exactly. So it's going to be continuous from negative infinity to 1, union 1 to 2, union 2 to infinity. This is where it's going to be continuous. So if that's where it's continuous, I know it's going to have discontinuities. Continuities. I think that's how you spell it. Discontinuities. Okay, cool. It'll have discontinuities. I know I'll have an infinite discontinuity at x equals 1, because that's where I have a vertical asymptote. And I know I'll have an infinite discontinuity at x equals 2, because that's where I have another asymptote. So I could have an infinite discontinuity if it's approaching like they're both going towards positive infinity, both going towards negative infinity. Maybe one's going towards one and the other is going towards the other. Literally, when you're approaching an asymptote, that's when you're just going towards infinities. Cool, and then that's it. That's all we had to do for A. We found the interval of continuity, right? That's all the unions. So we know wherever we have an asymptote, it won't be continuous. So I just cut out the places where x has an asymptote. We found the points of discontinuity where I have those two asymptotes, and where you have asymptotes, that's where you have infinite discontinuities. So notice we do not have a jump discontinuity, because that would mean we'd have to have a piecewise. We don't have a removable, otherwise we would have had a factor that canceled out. And then you only get oscillating discontinuities if you have a trig function. Yeah. Cool?
Always? Like whenever there's a trig function?
Well, if you have like sine of 1 over x, sine of 1 over x squared, cosine of 1 over x. Like because most times the oscillating, it's always like going up and down, and you have oscillations when you're doing trig functions. Okay, let's try the next one. Let's try b. Do you guys need me to leave this up a little longer? I think it's enough time to write. I've talked a lot. I'll just leave it like this. Okay, y equals absolute value of x minus 1. So I don't have a fraction, so I don't think I'll have any asymptotes. Because what does this look like? How is this different than the parent function?
It's just
It's literally your absolute value function shifted over 1. It's your absolute value function. Zero, 1, okay. So does it have holes? No removable discontinuities, no infinite, no jump, no oscillating. So it's going to be continuous the whole interval. So I can say, oh my gosh, I can say continuous on negative infinity to infinity. Literally, give me an x value, we can plug in, and I will find a y value. There's no number where if I'd plug in x, it would say undefined. Right? So every single x, no matter what you choose, will spit out a y for you. Okay, so if it's continuous on all real numbers, guess what? There's no discontinuities. And that's all you'd have to say. No discontinuities. All right, y equals ln of x minus 1. So wait, we know how to graph ln. Roughly, what does ln look like? Well, we did it last year. First, what does e look like? If I have y equals e to the x, it looks like this. And guess what? ln is the reciprocal function. So if I draw the line y equals x, do you remember what a reciprocal function is?
It's going to be like this.
Y equals x. I reflected across the line y equals x. And instead, ln is going to look something like that. Woo. Hold on, I have to make it exact. So this is ln of x. Here was e to the x. They're reciprocals. So notice,
this is going to be something we have to know.
You have to know what ln looks like. Right, you should be comfortable with it. That's why we went over it before. Okay, so wait, if I had, did I have a horizontal asymptote with my e function? Yes, there's a horizontal asymptote at y equals 0. Do I have a vertical asymptote for my ln function? Yes, y equals 0. Yes, okay. So before, with my e to the x, I had a horizontal asymptote, but with my reciprocal function, I'll have a vertical asymptote. Do we remember vertical asymptotes for ln? Okay. This looks really messy. Let me just, I'm going to erase this, and then I'm going to redraw it, just so we don't get confused, because I had e to the x on there. All right, so we know roughly ln looks something like that. But the whole minus 1, that means I'm shifted to the right by 1. So where I used to have a vertical asymptote at x equals 0, now I have a vertical asymptote at x equals 1. So what this does, it shifts to the right by 1. Shifts right by 1. So here's 0, 1, so I have a vertical asymptote. And then ln always follows the vertical asymptote and goes like that. So it's literally not defined left of my asymptote. So I'm continuous on the interval from 1 to infinity. Notice they're both parentheses because I'm not including 1. If I would plug in 1, ln of 0, that goes to negative infinity. Do I have any discontinuities? No. Because it's really undefined left of it, you gotta be approaching from left side. Okay. And then D. Ooh, y equals e to the 2 over x. So I'm just going to rewrite it. So I'm going to zoom in a little bit. just so I have enough space. So I'll rewrite this just so we can see a little better. So y equals e to the 2 over x. So right away, we know we can't have the bottom of my fraction equal 0. So that means x cannot equal 0. What happens if x equals 0?
X equals 0, then
It'll be
it's
undefined because you can't divide by 0.
It'll be undefined. I can't divide by 0. Exactly. Do we know roughly what this will look like? There were calculators out? I say you don't have to have hats. Doesn't mean you can, like, not have your calculators. Guys, you guys. Okay. So, e to the 2 over x. E to 2 over x. So I see something like weird's going on at 0. Because if you think about it, as x gets closer and closer to 0 from the right side, 2 divided by 1/2 is 4. 2 divided by 1/4 is going to be to the 8. Every time I get smaller and smaller on my exponent gets bigger and bigger, and e to a large exponent goes to infinity. But on the left side, if I put it negative, it would be like 1 over e. That's why I'll have a asymptote. Yeah, I guess that was not a good explanation. But you can see like it continues. It's kind of hard to see, but the blue gets closer and closer to 0 here. Not a great explanation, but okay. So I see x cannot equal 0. All right, so we see it's continuous everywhere except that 0. So it's going to be continuous from negative infinity to 0, union 0 to infinity, because that's the only number x cannot equal. I can put in any other number, I'll have some y value. That's the only place where I'll have a discontinuity. And what type of discontinuity do I have? Infinite, because I'm going to infinity, and then on the other side of my asymptote, I'm like going somewhere else. Infinite discontinuity at x equals 0. Okay, let me take this off. Hey, and guess what pops up once again? Piecewise functions. This is why it was so important last year in pre-cal when I was going over piecewise. Because you gotta know it. I can't just stop and reteach it during calc. Alright, so let's graph it and answer the following questions. So first, between -1 and 0, I'm gonna have negative x squared plus 1. So we know x squared up. Negative x squared, down, and then I'm shifting all up by 1. So it's literally going to be a downward, remember, x squared, negative x squared, and then plus 1, move it up by 1. Dance party, but now you know. Try to make it like interesting, so you know, whatever. Okay, cool, so I'll have a hole here, and then I'll have a solid dot, and then it's just my start of my parabola. That was really ugly. So if I plug in 0, 0 squared, 0 plus 1 is 1. Okay, open circle, because I do not include my value of 0. And then I do include -1. -1 squared is 1. -1 plus 1 is 0. Okay, cool. And then what if I'm between 0 and 2? So x plus 1. So I start, interesting. Let me pick a different color just so you can see it. So I start here, oops, guess what? It literally fit in together just like a perfect little puzzle piece. And then I go up till 2, open circle. I literally look at my 2 ending, I plug them in, 0 plus 1, 0. 2 plus 1 is 3, I put those 2 dots. I make it closed circle if it's or equal to, open circle if there's no or equal to sign, and then I like connect them. If I have a line, like I do here, it's a straight connection. If I have a parabola like this, I do a little curve with it. All right. I think we're grooving so far. And then if x equals 2, my y value is 4. It's just 1 point. Equals 4, I do it closed, because it's just the 1 point. And then if it's greater than 2, it's just going to be negative x. So I plug in 2, guess what? -2. So 2 comma -2, I have an open circle. Oops, let me pick a different color. -2, and then it goes down, slope of -1. Let me pause here. There's questions. Now is the time. Went through each one. Cool. So you look at your two boundaries. You find what the y values were. You make it a closed circle if it's or equal to. Make it an open circle if it's just a greater than or less than. And then for our pink, guess what? It was a line. Straight connection. For our blue, it was a parabola. So it's going to be a curved connection. For our light blue teal color, it's negative x. That's just a slope of -1, and it's a straight line, goes down forever. Okay, so first question, does f of -1 exist? Do I have a function value for -1?
Yeah.
Yes. Yeah, the value is 0. Does the limit of 1 from the negative side exist? Right, so I just read this, right, my English to math. Does the limit of my function as x approaches 1 from the right side, or I'm sorry, from the left side exist? So I'm approaching from the left side. So I'm approaching from the left side. Does it exist? Yeah, it does. What is it?
2.
2. Awesome. 2. Okay, does the limit of 2 from the positive side exist? Oh, wait. I'm asking if it's continuous. Does the limit from the right side equal the value of 2? So I'm looking from the right side. Is this value the same as the function value?
No.
No, it does not. Because the limit is -2 and the value of f of 2 is 4. Those are not the same. Those are not the same. Not the same. So I see I'm not, I'm not continuous at x equals 2. Am I continuous at x equals 0? So here, literally, ready, shortcut for continuity. I'm asking if the limit as x approaches 0 from the negative side of my function, is this the same as the limit of my function as I approach 0 from the positive side? And is that equal to the value of my function? Yeah, it is. It's all three. Guess what? 1 is equal to 1, which is equal to 1. Cool. Yeah. Wake up. Let's go. No.
And if it said like
Got a lot of
x
coffee
equals
today.
12, then you would just do limit of x as x.
Yeah, if I said x equals 2, everywhere where I put a 0 would be 2. But like a lot of times, the interesting part's always like close to 0. Okay, let's try the next page. I think we're doing good on time. All right, find each point of discontinuity. Which of them are removable, not removable? Give reason for answers. Okay, so first, we need to graph it. So as long as x is less than 2, the graph is 3 minus x. So I plug in 2 for x. 3 minus 2 is 1. So I do 2, 1, open circle. And then whenever x is less than that, I'm going to follow this graph. So what if I put 0 in? 0, 3 minus 0 is 3. That makes sense because I have a slope of -1, a y-intercept of 3. So I'm just going to make it cheat a little bit. It's hard drawing straight lines. Okay, so there's that part. F of x equals 2 if x equals 2. Okay, so literally I'm just drawing one little point at 2, 2. And then, if x is greater than 2, I have x over 2. So this first one, I plug in 2 because that's my boundary. 2 over 2 is 1. So it's going to be, okay, so it's going to be an open circle here. And then I'm going up, let's see, by a half. So if I put in 4, so it's like this. So it kind of looks like an absolute value function. It's just the purple, the left side, has a slope of -1. The right side is a slope of like 1/2. So it's almost like a lopsided a little bit. Cool. So this x over 2 is the same thing as 1/2 x. Cool. So we know the slope is 1/2. Okay, so let's look at the different discontinuities we have. What kind of discontinuity do we have and where is it? We have a removable at x equals 2. So that was A, find each point discontinuity. We only have one, it's removable. B, which type Which of them are removable? Okay, well, guess what? X equals 2 is removable. That's it. And then give reasons for answers. So see the reason, guess what? We can say the limit as x approaches 2 from the negative side is equal, of f of x is equal to the limit of f of x as I approach 2 from the positive side, but, it is not equal to my value of my function at 2. So although the limit exists, it doesn't equal the value of the function. So that's why it will not be continuous right there. Okay. Questions so far? I'll give you a little more time to write this down.
Wait, doesn't it not equal?
Limit does not, doesn't. Thanks. Doesn't equal function value. Awesome. Is this like the 7th inning? Time to stretch. Stretch! Woo! 7th inning! Wait.
Okay, so it's not that like we have like extra.
You guys are so tired. You're yawning, draining my energy. All right, let's keep going.
Let's all just say.
Let's keep going. We only have three more pages.
Let's go.
3 more pages. Okay. Yes. Continuous function. So a function is continuous on an interval if and only if it's continuous at every point of the interval. Like, duh, that's what we've been doing, right? So when I was saying it's continuous from, like right here, when I was saying it's continuous from negative infinity to 1, union 1 to 2, union 2 to infinity, right? So when we did this problem earlier, we were implying that every other number, as long as we didn't cut it out, it would be continuous, all those numbers. Gabe, you want to sit up? Okay, so when I go back here, guess what? This is only going to be continuous everywhere where it's not discontinuous. Okay, let me rephrase that. A continuous function is one that's continuous at every point of its domain. It doesn't mean it's continuous from negative infinity to infinity. It just means for its domain. So if I say the domain is, well, for instance here, if I would say the domain is negative infinity to 0, union 0 to infinity, guess what? I could say it's continuous on its domain. I could be continuous on an interval if I'm continuous at every point of my interval. So I'm continuous every point that I've listed. The only point I excluded was 0, but that's the only point where I'm not continuous. Let me be clear with domain. So this does not mean continuous from negative infinity to infinity. Okay. Doesn't mean continuous. Yeah.
So like if I leave my my calculator here,
There's no cameras in here.
then why don't you say
I don't
I don't think we do.
We can put a camera any place except inside a bathroom. So we can put cameras outside bathrooms, which is what they did because they want to prevent kids from going in there with little jewels. So.
But then they put in one date to them.
They did. It'd be interesting to see how they tested it. Okay. Guys, I should just be a comedian. Let me quit. But it's all about... okay. What? Never mind. I don't know. Okay, let's go. A continuous function does not have to be continuous on every interval. For example, the graph below is literally y equals 1 over x. 1 over x. Hyperbola, whatever. It's a continuous function. However, it's not continuous from negative 1 to 1 because that's discontinuity at x equals 0. So it's continuous everywhere except for that small little chunk. Cool. So this is not really anything new. So let's go through different theorems. Properties of continuous functions. Okay. If f and g are continuous, so if I have two functions and they're both continuous at a single x value, then we can say, guess what? The following combinations are continuous at the same x value. So what I just did, I described this in normal English. Let me do it one more time. I'll read it and then I will translate. If f and g are continuous at x equals c, then the following combinations are continuous at x equals c. Okay, cool. So I have two functions. If they're both continuous at this single x value, then guess what? I can say the following things would also work and still be continuous. So I could take the two sums. I could take the sums of them. I could subtract them, the difference. I could multiply the constant multiple. You see that's something that pops up a lot. And quotients as long as I'm not dividing by 0. Okay, so I mean the best thing to do would be do some examples. But we are going to. Because reading this does nothing for me. Doing the problems, you're like, oh, now I see what you're talking about. Like, that makes more sense. Theorem 7, compositive continuous functions. This is why we really reviewed composite. Because remember Fogg and Goff?
Yeah, fuck off, yeah. Fuck off, man.
I don't know what I expected. Okay. So this is the same thing as f of g of x. Remember? Okay, and then if I have Goff, this is the same as g of f of x. Cool. So if I'm continuous at a point C, if f is continuous, if my first function is continuous at that x value, and g is continuous at f of c value, then the composite is going to be continuous. So what we have to do is if my inside function is continuous at that x point, and then I have the f of x value at the x point, right? I have the y value, and then I plug it into my second function. If that's continuous, then the whole composite function will be continuous. Okay, so what does this even mean, right? Let's try this out. So f of x, here I have this little nice function, sine of x squared plus 1, that definitely looks like a composite function. Maybe. Yeah? Composite function. Look. Who would have thought? Do an example right after we talk about it. Composite function. So I could say h of x is sine of x, right? That's my outside function. And then my g of x, the inside function's x squared plus 1. So it's kind of like I took h of g of x, right? Sine of x squared plus 1, right? So that's equal to my f of x. So as long as, sorry, I'll let you write this down. Give me a second. Okay, let's think about what we just said, right? With theorem 7, composite of continuous functions. So we said if the inside function is continuous at g. So is my inside function, is this continuous? Yeah. So from up above, this is my inside function. It's always continuous. X squared plus 1 is a parabola. It's always continuous. Okay, so it's always continuous. And then, so this means the composite is always continuous. Explain why the given function is continuous. Okay, cool. So we know that sine of x is continuous, right? Sine of x goes on forever in both directions. Let's try it again. Do it with me. Goes on forever in both directions. Okay, cool. What about x squared plus 1? X squared plus 1 is forever. It's continuous. Okay, so wait. If both functions, h of x and g of x, are both continuous, that means my whole composite function is also going to be continuous. Is also continuous. Okay, cool. Last page. Woo.
Yeah, it's a freaking roll.
Well, because people are falling asleep, so.
What would you rather not?
Well, I mean, I'd want you to be awake, so you can like pay attention and learn the stuff. No, there's not.
Remember when you always just like go through? No.
Called?
Yeah.
Called out. Okay.
No.
Called out.
Oh, you wanted to know that.
Dear mate, the intermediate value theorem for continuous functions. Did we go over this already? No. Did you learn about this? False. You definitely learned about this last year. I remember this. All right.
I didn't know.
Call it IVT, intermediate value theorem. Gabe, you were either sleeping or you're talking to Elliot. This is a problem. This is a problem.
Busted.
What are you doing? Can we just not like be distracting of others? Can we like stop? Okay, thanks. Get your notes out. Let's write. Okay. Intermediate value theorem for continuous function. So I have a function y equals f of x. It's continuous on a closed interval. Cool. So there's no holes, no discontinuities. It's just smooth, continuous. I can be mad when you full goal, full. Okay, I can't be mad at that. Okay, so we're on a closed interval, we're continuous. So look at this closed interval from x equals a to x equals b. See this nice smooth function, no holes, right? It takes on every value from f of a to f of b. So I have a x value. Here's where I'm starting, x comma y. Here's my final, right? B comma f of b. So if I take an x value that's between my two boundaries, guess what? The y value is also going to be okay. Okay.
The thing about it is that Noah always gets this.
I made it. I don't think that is down the ramp.
Literally, all I'm saying is like, hey, here's the two n values. If I say this is like 4 and this is 6, I could have like my y value of c will be somewhere in between there. So my function takes on every value between the two y values. So if I have y naught, which is my y value of my x value that's in the middle, and if it's between, then I can say it's equal to f of c for sub c on this interval. Okay, whatever. Let's do the example. Find the value for a so that the function is continuous. So remember, we want to graph this, and I want the end value of my first piece to match the begin value of my second piece. Because otherwise I'll have a jump discontinuity. What I'm wanting to do, what I'm really asking here is, hey, make the jump, make my piecewise, so that way I don't actually have a break. Okay.
So then you would have to plug 2 into both of them. Or replace. No, you would have to plug 2 into the first one, and so you get 7. And then so that has to equal 2, 7, 2.
So I want my 2x plus 3 has to have the same value as ax plus 1.
Right?
So 2 times 3 plus 3 should equal a times 2 plus 1. Because I'm trying to solve for what value of a will make it continuous. And if I have the same y value, it'll make it continuous. Is this what you're saying?
Is a 3?
Yes.
Okay, so you do 2, you plug in 2, because since you said they need a match, so it's 2 times 2 plus 3, which is 7. So that one
2 times, oh, wait.
one is 2 comma
I put
7.
in, oh, it's not.
That's why it's confused by what?
Sorry.
Yeah, so then it's 2 comma 7, and so you need the bottom half to also equal 2 comma 7.
Yeah.
So what times 2 plus 1 is 7, and it's 3. Right?
Yeah, it's 3.
Good job now.
So literally, let's see. So 1, 2, 3, 4, 5, 6, 7. 1, 2. So roughly, this is what the first part of my graph looks like. And what we really wanted to do was figure out how would I make this continuous. So if I had this be 3x plus 1, well, at x equals 2, that would make it a whole at 7. And then it continues on like that. So I wanted it to overlap at this point. I wanted the gray one, the first one should be a closed circle, and then my open circle should go directly around it. That way, I don't have a jump discontinuity. It like continues on going. So since I wanted the y values to be the same, I set them equal to each other and find out what y should be so that way they match. Okay, so this is your assignment. Wonderful. You do have 8 minutes left of class.